Thank you all for coming. I'm Alicia Frame, and I'm joined by Omkar More. And we are here to tell you about fine-tuning and reinforcement learning. So I am the product lead for model customization. Omkar is my engineering counterpart. And what we're going to tell you about today is how you can deploy, observe, and learn from your production agents to get better, smarter, cheaper, and faster models. One thing just to call out before I get started is it's a little noisy in here. If you're having trouble hearing, there are headsets in the back that you can get so that you can kind of cut through the background noise. But I will try to be super loud so you can hear me. And with that, let's get started. So what are we going to cover today? We're going to start with the basics, 5 minutes of slides, and we're going to talk about what is fine-tuning, why fine-tune, and what does this have to do with production agents? From there, we're going to get started with the demos. The first demo we're going to show you is how you can use a technique called distillation to create cheaper and faster agents. Next, we're going to deal with what if your teacher isn't smart enough? How can we use reinforcement learning to learn from our mistakes? After that, one level harder, we're going to talk about interactive reinforcement learning, and you're all going to get a preview of our new low-level training API. Think of it as PyTorch as a service. You get access to the low-level training primitives. We manage the compute. We build better models for you. And then after you've kind of had a little bit of a panic attack of, wow, that was a lot of content, we're going to end with coding agents for fine-tuning and show you how you can use our fine-tuning skill to really use natural language to describe your goals and create better models in minutes. And with that, let's get started. So before we dive in, I want to kind of situate you in the bigger picture. We're part of the Microsoft Foundry team, and Foundry gives you your agent platform. The foundation is models. So there are over 11,000 models in Foundry, and these models power our agent runtime. Lets you deploy and host your agents, observe them, give them tools. And once you've got those agents, we want them to be better and smarter. So we offer tooling to evaluate them, know if they're doing what you want them to do, and optimize them, improve their performance based on what you've observed. This talk is really going to be focusing on the evaluate and optimize box. But I want to kind of motivate this talk and explain why we're here. We've been working on fine-tuning for a while, and I feel like people are finally starting to listen to, like, there is a reason to customize models. And what we're seeing now is agents have taken off. Agents helped us make this slide deck. Agents helped us make this demo. A third of enterprise software apps say they're going to embed agentic AI within 2 years. I think that's wrong. I think the number is higher and sooner. Half of teams already have some kind of production agent today. The problem, agents consume 20 to 30 times more tokens per turn than an old-fashioned chat interaction. And so all of a sudden, we have way more models being deployed for way more use cases, consuming way more tokens. And all of a sudden, we've broken the bank, you've run out of tokens, your credit card is maxed out. What do we do? And so if agents are token-consuming machines, fine-tuning lets you create a reliable agent without breaking the bank. And so what does fine-tuning do? When you customize a model, you can create a cheaper, faster, smarter model. So historically, I think when people think about fine-tuning, they think about improving model quality. 2 years ago, a lot of people said, like, wow, I need to fine-tune GPT-3.5 to teach it about my domain. Today, when we talk about improving quality, especially in the context of agents, it's really about call the right tool at the right time with the right inputs. Improving quality is really about baking in those instructions from your prompt into the weights of the model itself. And that is super important, but it's not the full story. What we're seeing more and more of, and you saw this probably in sessions where we talked about Harvey or UiPath, many companies are fine-tuning smaller, cheaper, faster models to power their production agents for their use cases with the same quality as a frontier model at a fraction of the price. So the targets of fine-tuning are often 10 to 30 times cheaper than a frontier model. So we're talking about replacing GPT-5.4 with 4.1 nano or a Qwen model, something much cheaper. And so when you're looking at something 30 times cheaper, even if it's consuming 30 times the tokens, your budget still balances. The other thing we worry about with agents is they're chatty, but we're impatient. The big frontier models can be slow. We've all sat there and kind of watched Claude churn, and you're like, I'm bored, come on. Small models stream tokens faster. So your agentic workflows, once you've got that smaller model, it responds more quickly. So you really now have kind of the perfect solution, right? You've got a model that knows what tools to call and how to behave, and it's cheaper and it's faster. And so because of this, we're seeing a lot more traction for fine-tuning and customization. When we talk about optimization, it's really a journey. So in Foundry, you often start from, I built my agent, I've got to get the prompt right. Can I give it instructions to make it do what I want? Step 2 is, okay, I need to add context management to my agent runtime. I'm going to give it data, grounding, and memory. And then I can give it tools so it can take actions and call external things. And then all this time, I'm evaluating it. I'm checking if it's doing what I want. I'm checking how it's performing. Once we've got that, though, now it becomes time to optimize. Is my model doing the wrong stuff? Is it too expensive? Is it too slow? And that's where fine-tuning comes in. And so this talk today is really going to focus on this right-hand side of this optimization curve. And I already said, fine-tuning is becoming more popular as we see the rise of agents, and we're seeing this in kind of the developer world. About half of developers say that they want to replace their out-of-the-box models with fine-tuning. 3 years ago, maybe 4 years ago, people were like, I'm going to build my own foundation model. And then we kind of moved on and everyone said, you know what, out-of-the-box models are amazing. I'm good, I don't need to do this. And now people are starting to look at their balance sheets or their CSAT and they're saying, actually, maybe fine-tuning is for me. And this really gets back to the cost compounding in the agency loop. And it ends up being about quality, latency, and cost, all driving people towards this decision. And now I've said the word fine-tuning like 30 times, and some of you, probably anyone who is not a data scientist, is like, what is fine-tuning? So I got to this a little late, but fine-tuning is really just your cheat code to building a foundation model. So if we go back to where do these models come from? The way you build a foundation model is you start with pre-training. You have a massive amount of unlabeled data, and you start off by figuring out next token prediction. So I've got one word, what's the next most likely word? Once you've got that, you often use instruction tuning, where you give prompt response data, task-specific data to teach the model how to respond. And then the final step is going to be alignment tuning, where you give the model human preference data, reward models, to really steer how you want it to respond. You put these 3 steps together, you get your frontier model. Fine-tuning lets you kind of skip the most expensive, hardest, complicated part. You pick up your generic off-the-shelf model that's pretty good. And then you get to choose, do I want to do supervised fine-tuning, so teach it to behave in a certain way, give it data to copy and learn from, or do I want to align it, or do I want to do both? And so you kind of get a head start in the customization journey, add your data, and create your own IP. And so with that, we've kind of given you the crash course in fine-tuning, and we're going to get to the first demo, which is, I'm sure, what you all care about. And so point 1 is we're going to do cheaper and faster. So a really common technique in the world of model customization and fine-tuning is distillation. And this is where you take a large smart model like GPT-5.5, and you capture its traffic and use that as your training data. What we're going to show you is how you take traces from your production agent, filter and curate them, create a training set, and from that, generate your small fine-tuned model that is just as good as your high-quality frontier model. So with that, we're going to switch to the demo.
All right. So throughout this demo and throughout the talk today, we're going to show you a variety of techniques for post-training. with the intention of making all your models faster, cheaper, and smarter. So across all of these demos, we're going to concentrate on a single customer scenario. This customer scenario is about building a customer service agent for a retail scenario. So let's say you have a retailer and you have a customer service agent that processes refunds. So customer calls in, asks for a refund for a particular item. The agent has to go ahead and decide whether the request was valid. It has to decide whether the item could be returned. It also has to decide whether the item should be replaced or refunded. So these are complex scenarios that the agent has to navigate. The agent can look at the order details via a tool. It could also go and look at the fulfillment status. It could go and look at the policy details and then process the payments. But what if it gets wrong? If it gets it wrong, it could lead to the retailer losing a lot of money. And as you know,
or a lot of customers.
Or a lot of customers. And online returns is about $900 billion a business in US last year. So it's very critical for us to get this scenario right. So with that setup, let's go ahead and look at how we can do distillation from a larger model like a 5.4 model to a smaller 4.1 or 4.1 mini model and see if we can get the models to be faster and cheaper. Okay?
Okay.
All right, so I have over here, let me go over to, all right. So let's go to our agents. Okay.
And so as you're pulling this up, for folks who haven't used it before, this is our Foundry UI. This is a really simple kind of no-code way to build agents, fine-tune models, but this is also all possible from code.
Absolutely. So to start with, I have built a hosted agent. So Foundry allows you to use any platform that you want, any agent platform like semantic kernel, if you want to use LangGraph, and host your agents on Foundry. So I've done that over here. This is an agent that is using GPT 5.4 as its base model. And let's try it out with an example. Not this one. Maybe this one. All right. So the customer is asking to return a yoga mat, which they have not used, and see if they can process a refund. Foundry hosted agents allow you to actually capture all the traces so that you can use that to evaluate and further use it to fine-tune as well. So as you can see, the request has been resolved, and you can look at the traces to see what exactly happened during the entire process.
So can you show us the tools that your agent is calling in here?
Absolutely. So here's what has happened. So if you see, the user view shows you what the request was and what the final outcome was. But the trajectories actually show you which all tools were invoked. In this case, the get order details was invoked. After that, we had the fulfillment status invoked, and then the check resolution policy. And then the final outcome was resulted. So this is really rich data that you can use to evaluate your models and also use it to improve them. So going back, let's go ahead and look at the traces tab in hosted agents. You will see that this agent has been working for the last few days, and we have about, I think about 1,000 odd traces that have been captured. And we'll use these to actually go ahead and evaluate the model. Now, the first step to think about this is, can I just replace my large model with a smaller model and see how it performs? So let's go ahead and build up an evaluation scenario and see how do they stack up in the first place before we do any fine-tuning whatsoever.
So really, you're basically showing us that we're not lying. We're going to start with no fine-tuning, just smaller and cheaper. Let's see how well it works out.
All right, and this I'm going to do it with the SDK. So let's go ahead and start that up. So a few things to talk about over here is, so let me just start off this, and then we can.
So are you loading up all of your evals to be able to check how well the models perform?
Yes. So now Foundry allows you to have different graders. So it allows out-of-the-box graders like task resolution, intent resolution. So these are LLM-based graders that can look at the trajectory and tell what the intent was and was it actually done or not. So you could use that. Or you could get more control by writing your own graders. And we allow you to write graders backed by an LLM or using pure Python code itself. So in this case, I have written a Python grader, which allows me to grade the responses on 3 fronts. Whether the decision was right, whether like in case the refund was supposed to be done or was it rejected. So I give 50% weightage to that. How accurate was it? Like if I was from the dollar amount. So if it was $50 item, was I refunding $500? So that kind of thing. And then it also grades about 20% weight for the format itself, because this is important, because your downstreams are dependent upon how the model format is given.
And really, without this, we have no way of knowing, 1, if the agent works or not, but 2, whether fine-tuning makes anything better or worse. So this is really kind of the most foundational step.
Yes. And then I build an evaluation which has all of these 3 graders, and then submit an eval run for the base models. And let's go ahead and have a look at the evaluations themselves.
And so whenever you're generating something from the SDK, it's automatically registered in the UI. So if you want a beautiful view of your eval, you can just click over here and see it.
Yeah. So as you can see, the 04 Mini and GPT-5.4 do reasonably okay, 65% quality score. But the smaller models, which is 4.1 Mini and Nano, perform really poor. And you don't want to replace them as is, just to save cost and latency. So what do we do?
Cry?
Well, Foundry to the rescue. You can actually use the traces that we have captured to fine-tune a smaller model and see how it performs now. And they make it so simple that you can actually do it through the UI directly. So let me go ahead and show you just that. So go to retail. This is my agent. We go back to the traces that we saw earlier. And then click on the Create Dataset button. This allows you to convert your traces from raw traces into datasets that you can use for evaluation, for reinforcement fine-tuning, or for supervised fine-tuning. So it does a little bit more smarter things here. It removes all the duplicates. Your trajectories might have non-interesting conversations that it can be taken off. It will redirect some of the PII information as well before it uses it for training. So I'm going to go and try to do supervised fine-tuning over here. You will see that we have, let me see. Okay, hold on. All right, so as you can see, I have about 1,400 traces here. Supervised fine-tuning, we suggest you at least have about 1,000 samples. When you go to reinforcement fine-tuning, you will see that we can do a lot more with the smaller data set as well. So I'm going to use 1,000 samples for here, and then click on Start Fine-Tuning to start the wizard right here. Let's go ahead and select maybe GPT 4.1 Mini or Nano. You'll see a few options that you can select while you kick off a SFT run as well. So for instance, the training type gives you different SKUs that you can use to govern data residency and your cost. My favorite over here is the developer preview, which allows you to do training at half of the cost of a standard tier job.
So if you're worried about fine-tuning being expensive, developer tier, 50% off.
Yeah, it runs on our low priority VMs, so it could take a little longer, but for developers, it's pretty good. We also introduced at build today the data zone SKU that allows you to have residency guarantees in US. So I'm going to use maybe just the standard for now. Also, you'll see that the data sets are already preloaded converted from the traces into here, so you don't need to go ahead and add any data sets. Then you can click on over here to have an automatically deployed to a model after job completion. We'll skip that for now. And you'll see that we have a few hyperparameters that you can tweak. And for higher and more control, you might need more hyperparameters. We'll show in the next few demos how you can get more control onto your fine-tuning process.
But here is really just easy mode, right?
Yes. So you can just go ahead and click just a few clicks, and then your training is started. Let's go ahead and open up a run that is already completed. So this is a distillation run that we did earlier, and you can go ahead on the monitor tab to see the scores. You'll see that there is the loss is reducing, accuracy is increasing, everything looking good. You can see that not just the final model, you'll also get checkpoints for interesting cases wherein the reward might have increased before the last step. You can use that to deploy and have a model as well. Or if you think that you need to further fine-tune this with more data, you can use continuous fine-tuning and go ahead and submit another run. In this case, the run looks pretty good. I have actually gone ahead and deployed this earlier. I have created an agent on top of it and ran the evaluation just in the interest of time. And we can go ahead and look at that evaluation run right now to see how it stacks up. All right. And let's go ahead and sort it by detailed order. OK, so as you can see, we have a new winner. So GPT-4.1 mini fine-tune actually outperforms O4 mini and 5.4 as well. So which is amazing. Now you have your agents.
Fraction of the cost.
Fraction of the cost. Your agents are faster and cheaper.
And I guess maybe
slightly
a little
more performant
smarter.
as well.
And the other thing I want to call out is you did include those default graders, right? The intent resolution, task completion. And what we can see there is like we're not trying to fine-tune to improve those, but our fine-tuning hasn't eroded the base model's capabilities. So like one fear with fine-tuning is like, maybe I made it better at this, but worse at other stuff. But we kind of have those guardrails in place to make sure that didn't happen. So that was awesome.
Thank you.
So what is our current leaderboard? 74%. That's an improvement, right? We've brought down our budget. We're still kind of holding with that frontier model standard, but $900 billion, 74% of that, we're still losing over $100 billion with spurious refunds. So what do we need to do? Sometimes your teacher isn't smart enough. So with Distillation, what we just showed you, where you have your teacher model, frontier class, generate a bunch of data, fine-tune a small model using supervised fine-tuning. With those techniques, super easy to do, but you're really never going to get smarter than your teacher. The source of the training data, the mark you're trying to hit, is the teacher performance. But for us, if we look at this and say 74% is really not good enough for our business, we need a new technique. And that's where reinforcement learning comes in. And so in this scenario, what you're doing is the model itself learns from its own mistakes. So we define a grader, and so all the work we put into evaluating the baseline, evaluating our fine-tuned models, comes in handy. We use that same grader to score the model's own responses and learn from those scores. So your model generates sample results, you score them, you learn from the best performing results, and the model over time learns how to reason, in this case, through multiple different tool calls that it has to chain and put together. The one caveat, though, for reinforcement learning is most of the time, it needs to be a verifiable task. So what you're doing is you're grading if the response is good or not and learning from that signal. If you can't grade it, you can't learn from it. But the good news is, like, refunds are gradable. You can look at it and say, yes, you should have refunded that, or no, that was terrible. And so this is a perfect scenario where we can score whether it's getting better or worse. So next demo, reinforcement learning, learning from the agent's mistakes. And so before we dive into the tech again, I'm going to just spend 30 seconds explaining kind of what's happening under the hood. So with reinforcement learning, you send your prompt to the model, and the model generates multiple samples. These are called rollouts. And so here the model has generated 3 possible samples. The grader you defined scores those samples. And the quality of your grader is basically going to determine whether this works or not. If there's no signal, if your grader is just like everything is wrong or everything is right, there's nowhere to go. So you need a grader that 1, grades the outcome you want, and 2, leaves room for improvement. So you need an initial signal, and then you need to iterate from there. Once you've got your quality score from your grader, that information is fed into your trainer. You reinforce the correct answers, you learn from them, and the model learns to reason about a new domain. And if that sounds a little complicated, Omkar is going to show you how simple it is to do in our UI.
Thank you, Alicia. So let's go ahead and look at reinforcement fine-tuning. So we saw in the previous demo, we took a teacher model. The teacher model had the entire trajectories spelled out. So what tools were supposed to be called, what was the responses, all of this was spelled out, and that was the training data set that was used for fine-tuning. Supervised fine-tuning is like learning by seeing or copying what a smarter person is doing. But in reinforcement fine-tuning, what we do is we don't give the exact trajectories or prescription of these are the tools that needs to be called. Instead, we give ability for the training process itself to invoke these tools on the fly, and then take the responses of those tools and use that to grade against the grader that we wrote in the evaluation flow, and see which of these responses are giving better results, and then continuously trying to find out or reason about it to make better decisions.
So you're giving the models the tools to answer the questions, and the model figures it out on its own.
Exactly. So now let's go ahead and see how you can do this in Foundry. So I'm here with the SDK. So let's go step by step. So we're going to have the configuration done. And one thing that you want to know over here is look at the training and the validation data. This data is again coming from the traces itself. But the training data right now doesn't have the entire tool call history. It only has the message, the actual message that the user had asked. And then it has some ground truth that will be used by the grader to grade this. So instead, for instance, you will have the final score that has to be defended, but it wouldn't have which tools to be called to get to that thing. It wouldn't have the message body itself that needs to be written, and so on. So we do this, we upload it to Foundry, and then let's go ahead and look at the most important part, which is the RFT grader. So you can use the evaluation grader that we already wrote itself, or you could tweak it as well. So in this case, I have added some coverage to tools itself, so which exact tools are getting called. So for instance, I don't want to have a high score for a response where the get orders is not even invoked. So in those cases, I can have control over how I want the grader to behave.
And this is really important for avoiding things like reward hacking.
Yes.
So like a failure mode when we were working on putting this together was the model would get things wrong and just learn, I will never call a tool, because it was getting penalized for calling the wrong tool.
Yes, and you'll see that. Yeah, and when we will see the run itself, you will see how you can avoid this by looking at our telemetry and the metrics that will tell you when such a thing does happen. All right, so now we said we need to give access to the tools to the training run itself. How do you do that? So in this case, I have hosted all of these tools on a function app, and these function apps can be invoked. These are real tool calls that can be made. It has some of these information. It's like your RL harness or RL environment, so to say. You could also use MCP servers or anywhere else you have your tools hosted. And let's go ahead and kick off a run. And let's go ahead and look at this run through Foundry to see what were the hyperparameters and how an earlier run has performed. Okay, this is queued, so here's a completed run. So you get a few more things here. So you get access to a few more hyperparameters that are specific to reinforcement fine-tuning, especially to a reasoning model like 𝗀𝗄𝗏. You get to choose what is the reasoning effort the model has to put in. You can set it to low, medium, or high. This tells you how much chain of thought the model has to do so that it can come to the right answer. And this has implications on what your token cost is going to be as well. Next up, you can also change the number of epochs, evaluation interval, and things thereabout. You will see this is how I have configured the tools to be called to the function app.
And so this really tells the training run, these are the tools you can use.
Yes, this is the real training run. When the training is happening, the tools are getting invoked, and then those results are what is getting used, rather than just copying like in supervised fine-tuning. Let's go ahead and look at the monitor tab to see what the results look like. So the primary metric that you want to look at is rewards. Are the rewards increasing over time? And are the rewards increasing for your validation set over time? As you can see, we are, that looks good. Both the train and validation rewards are increasing. The other interesting thing to notice here is the reasoning token mean per step. You can see that the model was trying to spend a lot of reasoning effort early on in the training process, but as it goes on, the reasoning effort comes down. So this again has implications in terms of how much tokens will be used by a fine-tuned model, because now the final checkpoint will use a lot less reasoning than the base model itself.
And so early on, it's just calling a whole bunch of different tools, trying to figure it out.
And the other thing you would look at is the number of tool calls per rollout. So in case if it determined that, hey, I don't want to or penalize tool calling itself and then stop calling tools altogether, you will notice a dip over here and then say that, hey, there's something wrong with this run, and you would want to iterate on top of your grader to tweak these things. Okay. So with that done, let's go ahead and look at the evaluations on how this model fares amongst our leaderboard. So we have done the distillation, we have looked at the RFT evals. Let's go and check it out. So again, we have a new winner. We have 𝗦𝗽𝗲𝗸𝗀𝗀𝗀 coming up at 84%. So that's a huge pump up from where it was at 75, 73%. And the intent resolution and task completion are also increasing or maybe staying stable. So this is how you can use, like, the more effort that you put in, the better what you get. So for instance, reinforcement learning can be a bit of an effort to kind of get it right, making sure that your model graders are correct. The runs can take a little longer, but the outcome is also substantial.
And importantly, we're still keeping true to that better, cheaper, faster, right? Because
Yes.
𝗦𝗽𝗲𝗀𝗀𝗀 is still a smaller model than 5.4, which is our teacher.
Yeah, it's substantially cheaper than 5.4.
So going back to, if you saw in the keynote, that hill climbing narrative, we're kind of on our way up the hill. And before we kind of dive back into more demos, I do like to take one moment to share like some real world use cases. This is not just demoware. This is not just us making up a new use for some stuff we think is cool. We have customers using this in production. So 𝗦𝗲𝗀𝗀𝗀𝗀, they build actually customer support agent as a service. They used distillation and fine tuning on Foundry to power their service, switching to smaller, cheaper, faster models. Discovery Bank used distillation and fine tuning to create a smaller, faster, lower latency model to power their banking app. This was a scenario where customers were texting the app and getting a response, and they went from 6 seconds down to 1.5 seconds. And for like customer satisfaction, that's huge. And DocuSign is probably one of our biggest token customers. They were able to distill and see a 50% reduction in cost for AI document processing. So distillation, fine-tuning, reinforcement learning are really critical tools in the toolbox for making agents economically viable and delightful to use. So we're still only at 84%.
Yep.
That's still maybe $90 billion lost. So what if we need more control? Mostly what we've showed you so far was super simple UI-based high-level APIs. Some of you, if anyone here is a data scientist, an AI scientist, is like, I want to define my own rollout environment. I want to define my own algorithm. I want full control over the hyperparameters. And if that is you, get excited. We're going to give you a sneak peek of our new interactive training API. Before we show you what it is, it's helpful to just kind of compare and contrast how the two different services work. So everything we've shown you so far is really managed fine-tuning. You are the user, you pick your model, you pick your technique, SFT, RFT, you provide your data, and you submit it to the service. And the service does the rollouts, grades the responses, does the loss computation, updates the weights, and kind of iterates as a closed loop before it returns a checkpoint. You can't mess with what's happening in that service boundary. Our new training API actually gives you much more control. You, as the practitioner, set up the config, the recipe, you invoke the rollout engine, you compute the loss, you update the weights, and then look, we're back outside that service boundary, so you update the grader itself. And the big difference here is you're controlling the algorithm, the training primitives, every aspect of the fine-tuning job, except the GPU infrastructure. So if anyone here has used 𝗲𝗀 or attempted to use 𝗲𝗀 and failed, we're abstracting away all the pain of figuring out how do I set up these GPU clusters, how do I orchestrate this, is this synchronous, is it asynchronous, is it aggregated or disaggregated? We manage that for you. You focus on the algorithm, the problem you're trying to solve, and we manage the compute. And with that, I'm going to pass it off to Omkar to show you what this actually looks like.
All right, thank you. So in the previous first two demos, we looked at the high-level APIs that Foundry provides. These are great for most of the cases and for most of the people. They are scenarios where you just do fire and forget. You give up the tool, you give the tools, you give the configuration, you give the data set, and then let Foundry do its job. But as I said, the more effort you put in, the more value you get. So if you put in a little bit more effort and want to do it yourself, we allow you to do that with these low-level APIs, wherein you write your own code, and you can use these smaller primitives for doing forward pass, backward pass, optim stage, sampling, things that are inherent that require GPUs. You leave that to us, and you can write your own recipes that will give you a lot more control. So in this demo, I'm going to use our fine-tuning fine-grained APIs to fine-tune a OSS model 𝗦𝗽𝗲𝗀𝗶𝗸𝗏 and see how it performs and stacks with a scenario. All right? So let's get started. But before that, just to kind of give you a visualization, what does a recipe really look like? A recipe has specific steps, like, hey, first you're going to take the data set, you're going to generate multiple samples out of it. So essentially, let's say one conversation request, you could have 10 or 20 samples generated. That's our different options that the model is emitting out. For that, you're going to call our sample API, which runs on GPUs where we have preloaded a base LLM model and give you the responses. You take these samples and then go ahead and write your own grader. You can invoke your own grader to see how these samples were behaving. And earlier, the grader was supposed to be limited to what we support. Let's say you want to write a C# grader. Let's say you want to write something completely different. You can use that. The tools, for instance, we required you to update the tools or upload the tools on an MCP server or something. Say you don't want to do that. Say your tools are in some format that are not compatible with our high-level APIs. You can use that now because you have full control over invoking of the tools in the sampling process.
Or I could even have interactions with an environment. So like execute the rollout, call real tools in the real world, and see what happens.
Correct. And then once you do that, this is the GRPO step where you compute the advantages, like basically take the mean of the samples and see which ones are better. And then use the forward-backward pass to go ahead and change the compute the gradients. Behind the scenes, we have two nodes. One is called the training node, and one is the sampling node. And in the training node, we run the forward-backward pass, compute the gradients, and then when you call sync, we actually sync these LoRa's to the sampling node. And all of this requires a lot of telemetry. Listen, it's a hard work that you don't have to do if you have to do it yourself. Let's say you could very much build it this way, but you have to deal with nickel issues. You would have to deal with VLLM issues, as you said. So we abstract all of this out for you. And once you're done, you can go ahead and call sync checkpoint and save the checkpoint for training later on. And the great thing about this is not outside of Foundry. All of this is within Foundry. So you will see this as a run on Foundry. You can use the models as any other model in Foundry. You can use it for with hosted agents. You can use it with evaluation. The entire ecosystem is right there for you. So with that, let me quickly run this demo, and we'll see. So I have this as a, let me just. So in here, I have a launcher script that actually launches the script, the recipe, and it starts as a tmux session that you can go ahead and look at. All of this is happening locally on your own CPU machine. You could run it on your own laptop. This is what I'm doing over here. Or you could use an Azure VM if you want to have long-running sessions. Now, when this is going on, you can go ahead and we ship a small local dashboard. This is because the training entirely is happening on your machines. All the logs, fine-grained logs, are there on your machine itself. And you can use that to see how things are performing. So with that, let me just open up the local dashboard that's running. And let me just select existed run. OK, so this is a completed run with our low-level APIs. You can see, I think hopefully it's visible. You can see that the reward and accuracy is increasing over time, just like we saw in the previous one. But you also get more details here. So for instance, you see that the entropy is reducing down. You'll see that the grand norm is reducing down. So all of this information is much more fine-grained that you get with this setup. You will also see the KL divergence. You will see the group composition becoming better over time as well.
So I have a lot more control over what I can even see about this run. So
yes.
like KL divergence is kind of #1 investigation for reward hacking. Couldn't see that before, now I can.
Yeah, and this allows you to have the full control of all the telemetry on your side. You can tweak, like say your recipe is ongoing and you midway decide that, hey, I want to change this to use a different sampling strategy. You can do that, and that's where the interactive RL comes into the picture.
Curriculum learning.
You can use curriculum learning to start with a very simple task and then graduate it to a larger and larger task. You can do that too. Say you don't like GRPO, you want to experiment with some other mechanism, PPO or DPO and things like that. You can change that, and you can still use these same primitives to tweak the way you want. So with that, let me get back to the leaderboard to see how this stacks up with our runs. And this is my final evaluation board, where you will see, hopefully, that we have been able to beat even the 𝗦𝗫𝗀 mini fine-tuned version with 𝗦𝗽𝗲𝗀𝗀𝗶𝗶332B. So much cheaper, smaller model, and your agents are faster, cheaper, and smarter.
Amazing.
Thank you.
And so we've now gone like full hard mode, right? We went from simple UI to congratulations, you are writing the training algorithm yourself. And so some of you who are not data scientists might start to feel a little anxious. I hear fine-tuning is great, but this sounds really hard. One common complaint we hear is like, I don't even have the data to train these models. Or something I hear a lot is, you know what, I tried fine-tuning once, I made the model worse. I am never doing this again. And the good news is we hear you, and we've added a fine-tuning skill. So you can use your favorite coding agent and natural language to tell it what you want to do, and it's going to figure that out. And since I said it's a PM skill, I am going to do this demo. And I actually don't trust Claude and Copilot CLI to do this on the fly. And because I am not running a fine-tuned model, it's a little slow. So I ran this ahead of time. But basically, you can see what I did is I said, hey, I've got a hosted agent here. I gave it the address of my hosted agent, and I told it what I wanted it to do. This is Omkar's first demo, right? I have an agent. I want to figure out how well it does. So step 1 is I need to make a grader. I want it to grade to make sure it's calling the right tools. I want it to give partial credit. Please come up with that grader and then report how well the model performs. And I don't have to learn the API, the SDK. I don't have to click around in that UI. All it's going to do is use the fine-tuning skill. It knows how to build graders. It knows how to call our APIs. And great, it's done the baseline for me. It came up with the grader, so it gives full credit if it asks for clarification or if it gets the answer right. It gives partial credit if it gets some of the tool calls. And then we go ahead and we grade the teacher model. So this is our 5.4. It's a little different because this is a little different every time I run it, but it gives a mean score of 8.37, pass rate at 8 of about 78%. Teacher model's doing pretty well. Good. Okay, step 2. I want to create my fine-tuned model. So I'm going to go ahead and kick off a distillation run. To do that, all I say is let's kick off a distillation run. I do say my goal is I want it to be cheaper and faster, and that's going to help it pick which models to fine-tune for me. I want it to take my agent traces from that agent I shared, export them, filter them, dedupe them, and kick off a fine-tuning autopilot run. What that's going to do is it's going to decide, based on my data and what I've described, which models to run, which algorithm to pick, and run a couple different experiments and see how it goes. And so what it's going to do is I had it submit those jobs, and in parallel, I wanted the same kind of honesty check that the base models, the smaller, cheaper base models, are not just great on their own. So I asked it to do the same thing we showed you earlier. Let's evaluate the smaller, cheaper base models, and we'll see how we do. And so it ran. It kicked off the baseline. And I ran this before the session, but you can see it got the base model evals first.
Thank you.
Then it finished training. And just like before, we have our leaderboard. I had a winner. I came up with a fine-tuned 4.1 mini. It picked mini and nano because I said smaller and cheaper. And it picked the hyperparameters on its own. And I can see that the fine-tuned 4.1 mini gets almost the same mean score, actually a slightly higher pass at 8. And so I was able to do that same distillation flow, but with totally just natural language. And this is part of the GitHub Copilot for Azure skill, or you can download a separate fine-tuning skill if you just want it as a standalone. And this really makes fine-tuning accessible and super easy. So anyone can fine-tune, and the cool thing is what it'll do is if these all actually just made it worse, it'll look at the logs and decide what it needs to do next. Generate more data, try a different experiment, and iterate until it gets it right. And so just to end, we want to kind of take home message. One thing we hear a lot, we're going to dispel 2 myths. The first is that I don't need to fine-tune anymore because frontier models keep getting smarter. Why would I need to fine-tune? And the real answer is yes, they're getting smarter, but they're also getting bigger, slower, and more expensive. And you saw in the keynote today, we can fine-tune small, cheap models to outperform frontier class models. And the advantage when you fine-tune is your IP, your business knowledge, your domain goes into your custom model. It's not going into that frontier lab's weights for them to make money off of you. You keep your IP, you get a smarter model and better performance. The other thing I want to touch on is often people say, okay, that was cool, you showed me some cost savings. It costs a lot to fine-tune. You have to pay to train, you have to pay to host. I don't want to do this. The real answer is Omkar already showed you developer tier training. That's spot capacity, 50% off. The median supervised fine-tuning job on our platform costs about $1. It's not super expensive. And we've introduced things like developer tier hosting where there is no hosting fee. So experimentation is really easy. It gives you the bridge to get to production. And from there, as your usage ramps up, you see substantial cost savings. And so with that, we're kind of at the end of our talk. We're going to take questions afterwards. Feel free to come up to us. But if you want to get started, here are some resources. The sample notebooks we showed you today are in this repo. You can sign up for the preview of what Omkar showed you with the training API, or you can learn more. And with that, we thank you for your time. And if you want to see other sessions, you can come to our lab. We're running 3 of them tomorrow. You'll get to do hands-on with the example we showed you in the demo, learn how to do reinforcement learning yourselves. And there are some other great demos, breakout sessions, and lightning talks that you should check out. So thank you so much.